Hello everybody, I'm Toby Delbruck, and together with Tim Yu, we're going to tell you about our work on self-calibration of wide dynamic range bias current generators. So why calibrate biases? Well, for a long time we've been building neuromorphic event camera chips and other chips, and we've included, for about 15 years now, programmable bias generators that generate the thresholds, the bandwidth, the refractory period. These bias generators cover over 7 decades of dynamic range. In a typical DVS pixel like this, which I won't explain in detail, it's important to realize that these bias currents ID, I on, and I off program the event threshold of the pixel, and the event threshold depends on the bias current ratios, I on over ID and I off over ID. And nominally, a program bias current has a nominal value like this, but because of dopant fluctuation, there's a random variation due to dopant fluctuation of these program bias currents. So the concept is basically to use a population of biases measured on a chip to bring all the generated bias currents closer together on that chip and therefore improve the uniformity of response. The previous stochastic iPod proposed by this paper here is too slow and takes too much flash memory for a practical application. Our concept, in contrast, is to use measurements of the population of biases on each chip to bring them closer together. We include calibration circuits are included in the bias generator, and the calibration is done by camera firmware and takes less than a minute. Result, as you'll see, is that is improved uniformity of responses across different chips and higher mass production yield. This slide shows the architecture of our coarse-fine bias generator. As you can see here, on chip we have a master bias that generates a set of 8 coarse currents spaced by factors of 8. Then these coarse currents are routed to a set of on-chip biases, about a dozen of them, and each bias then takes a fraction of its chosen coarse current. The result is that we get measured bias currents that look like this. Here is the fine code and here is the coarse code, or actually the bias current. And by varying the coarse code we get these different curves, and by varying the fine code we can choose a point on a curve.
Now let's talk more about calibration methods. The plot here shows a set of uncalibrated bias currents versus fine codes on coarse range 5. The difference here is probably coming from current mirror variation, so for simplicity, we assume that the bias current scales linearly and the slope difference caused by variation are constant. The calibration consists of 2 parts, work done during calibration and during operation. First, the largest currents of all biases are measured, and we get the I bias here. Then we find the smallest current on each group and use them as a reference, here the IREF. This way we can simply apply straightforward downscaling to all biases. We calculate the scaling factor S by using this equation here. And finally we store S onto the flash memory. During operation, we first read S into RAM. This only needs to happen once when booting the system. When we receive an input fine code, a new fine code is calculated by multiplying the input with corresponding S. By sending the calibrated fine code instead of the input ones, we can get the results shown here on the right. Apply this method to more coarse ranges, we get these results. Coarse ranges 1 and 2 can have values below the transistor off current. We did not enable shifted sources in this measurement, so the smaller currents could not be measured. For coarse ranges 7 and 8, the full-scale currents are too large for the neuron to measure. Using smaller fine codes, however, results in additional nonlinearity that will scale up and worsen full-scale calibration. Here, we show the spread of the bias currents before and after calibration on a single chip. The spread is significantly reduced compared to the before calibration, particularly for coarse range 5. Where the neuron can accurately and linearly measure the bias current. We tested this method with more chips, and the effect of calibration for 5 chips is shown here. Pre-calibration current variability of about 6% is reduced to about 2% for every chip. Overall, calibration improves matching by at least a factor of 3. This calibration could improve yield and uniformity of response of mass production neuromorphic chips. We gratefully acknowledge fundings from EU projects See Better and Visualize, and we thank you for listening.